Okay, again, I apologize for the English, but I hope this will be clear. So I'd like to speak with you today about applications of inverse methods in general and some specific applications in the upper atmosphere in work performed here in Peru. To motivate, I have an example that has nothing to do with the upper atmosphere. But suppose you had a pipe buried in the ground. And so this is the depth of the pipe. And you'd like to measure the weight that you observe and anomalies in the weight due to the pipe. Well, the weight is related to the depth of the pipe by this simple integral transform. And if you walked from left to right, you would measure deflections in the weight, plus a little noise. Now, you may like now to invert this problem and make an estimation of how deep the pipe is in the ground. And you may do that using a least squares approach, where you try to find a model of the depth that predicts the data that you've measured. And if you did that, it's very simple. We've all done something like this. You would get a result that looked like this. Now, you haven't failed. I promise you, if you took this model for the depth of the pipe and put it back in this formula, you would reproduce this. But of course, you have failed, because this looks nothing like the depth of the pipe. And the problem is, inverse problems like this one, and even simpler ones, are unstable. It's their nature. And so we have a very difficult time going backwards, although it's quite easy to go forwards. However, with some small modifications, one can actually recover models like this from data like this. And what we're trying to do is essentially avoid fitting the noise, assigning significance to noise which is not significant. These kinds of problems are familiar to us in the upper atmosphere. All of our problems suffer from what we call poor conditioning. So here's how inverse problems work. In science, we try to come up with theories that, given some understood conditions, predict data. That's the scientific method. Very often, though, what we do is different. We have some data, we have a theory that we like, and the idea is to recover the conditions that are described by the data. So this problem can be discrete, so it looks like a matrix problem, or it can be continuous. If it is continuous, we typically just discretize it. The problem can be linear or nonlinear. If it's nonlinear, we typically linearize it and then proceed by iteration. Examples of these kinds of problems include Fourier transforms, Abel transforms, Radon transforms, Hilbert transforms, and just simple convolution. If you have an instrument, it has an instrument function, and the data that you get is therefore contaminated by a convolution with the instrument function. So we know how to go forward. Do we know how to go back? Given data, is there a prescription for using a model to predict the conditions that led to it? To understand this problem, we have to worry about the existence. Is there a model that exists at all? Uniqueness. Is there more than one model that does this? And most importantly, stability. Can we identify one model of many that is the right one? And describing this all is the so-called Riemann-Lebesgue lemma, which says if you go from left to right, the problem is stable. That's very good for the scientific method. It means that we have a hope of finding theories to predict data. But if you go from right to left, this is unstable. Very small perturbations, very small noise in the data will cause huge perturbations potentially in the model. And that's the problem that we have in data inversion. So there are three methods, or three names that people use to describe inverse methods. Some of them are called length methods. Here are some examples of applications for length methods. There are methods that are essentially filtering, where you try to filter out rapidly oscillating parts of the solution and leave behind the solutions that you want. And there are so-called MAP methods, maximum a posteriori methods, that are statistical in nature. And here are some examples of those. And I'll talk about all of these things, except that actually they're all equivalent, it turns out. So we can be happy about that. We don't have to learn so many things. If we understand one, we understand them all. This slide looks terrible, but it's actually not so bad. Many people use length methods to invert their data. And there are sort of three things that can happen to you when you invert your data. One of them is, n is the number of data that we have, and n is the number of unknowns that we're trying to find, and p is the rank of the G matrix that describes them. If you have more data than you have equations, the problem is overdetermined. And a characteristic of an overdetermined problem is that there's no exact solution. So an example here would be trying to fit a line to 3 data points. The approach that we take is called least squares, and what we try to do is minimize this, which is the chi-squared error, the model prediction error, the error between the data we predict and the data we have. And the model that does that, if everything is linear, is just this one. And we call this the maximum likelihood method, and this is a very familiar method. You can also have a situation where the number of unknowns you have is greater than the number of equations, in which case it's an undetermined problem, and the situation is the solution is not unique. So an example here is fitting a parabola to 2 points. We proceed by minimizing the length of our model, the Euclidean length of the model, minimizing some norm of the model. And this is consistent with Occam's razor. The simplest model is the best. And so this is a mathematical expression for what we minimize, and the model that does it is this one. Most often, though, for interesting problems, the situation that we have is we have more data and more unknowns than we have equations. This is called a mixed determined problem. It means it's both overdetermined and underdetermined at the same time. What it means is that there are no exact solutions and lots of solutions that are equally good. Here's an example of a mixed determined problem fitting a parabola to these points. What one does is one minimizes a combination of the model prediction error and the length of the model. And this is called weighted damped least squares. It's a damped solution. Here are the models that solve that. And the overall method is called regularization. And 0, 1, and 2 refers to the order of the length of the model that we're trying to minimize. Now, all of that is summarized in terms of singular value decomposition, which is something that many people are familiar with. You can decompose the G matrix into components. And the components are the 4 vector spaces that define G, the column space, the left null space, the row space, and the null space. And then these things are the singular values, which are like eigenvalues. And you can see where problems with uniqueness come in. If you have a model that projects into the null space, then that part of the model is zeroed out and it doesn't affect the data. So you can change the model by adding components to it, and if they project into the null space, it doesn't change the data. So we have a uniqueness issue. Also, an existence issue comes about if the column space doesn't fill the vector space, then there are elements of the data that are inaccessible. So we have an existence issue. Nevertheless, you can invert this. This is called the pseudo-inverse, the Moore-Penrose pseudo-inverse, and it gives us a formula for predicting the model. And this formula contains all of the formulas from the last slide. And it says the model that you want is the data projected into this matrix, weighted by the reciprocal singular values, and then projected into this matrix, so made up of the row space of G. And this always works. You can always apply it. And it deals with existence, and it deals with uniqueness. There's still a problem of stability, though. And we can understand stability issues from this. If some of these singular values are very, very small, then there's a huge amplification that occurs here. And if the noise that's present in the data projects into the column space, it gets amplified by these small singular values, and you have the noise being amplified hugely, and you have stability issues. So people talk about a condition number, which is the ratio of the largest to the smallest singular value. And if this number is very big, the situation is unstable. One way to proceed is to filter. You just artificially prevent these numbers from becoming too big. So one way to proceed is to just make the singular values not too big. You're essentially filtering out those components of the vector space that have small singular values, so you won't get amplification